Example 3 in 8.3 for Math 30-1 deals with, some variables in logarithms. And I have talked about this already, but if you have the log of any base of x, then what you would have to say is that that argument x must be greater than 0. Now that's the simplest way of stating this. What's really important is that as soon as the argument is more complex than just x, we might have to solve something. So if we look at in A, it does want us to state the restrictions on the variables. So I'm going to make each argument have to be greater than 0. And I know I wrote x is greater than 0 twice, but that's okay. So x squared, the argument must be greater than 0, x must be greater than 0, and then x must be greater than 0 there as well. I don't care the coefficient on the logarithm, that doesn't matter. The argument, what's inside the logarithm, must be a positive number or non-negative. Two different ways of saying that. It's probably been a while since you've solved these, but x squared is greater than 0. This has the solution when x is greater than 0 or when x is less than 0. Now, the concept here is that x squared and x must be greater than 0, so this does not form our solution. I can put -2 into this logarithm, but I can't put -2 into either of the other ones, just as an example of why we can't. So the restriction for this question just becomes that x must be greater than 0. That is the restriction. Now, you should tack on that it can be any real number greater than 0, but it cannot be 0 or less. All right, the next part of this question is really what I argue is more important, although restrictions do matter. I'm now going to try to combine this into a single logarithm. So I have log base 7 of x squared plus log base 7 of x, and then I'm going to write this last term as -5/2 times log base 7 of x. And the reason why I'd like putting that, 5 divided by 2 is 5/2 is it does make it a lot easier to make that coefficient an exponent. I think it's a good idea to leave the negative there. So I'm going to combine the two logs that are being added to each other. So this is going to be log base 7 of x squared times x. And then I'm also going to do my power log law here. So I'm going to be subtracting log base 7 of x to the power of 5/2. And again, I didn't take that negative with it. So it's almost like I treated this as a red bracket, and these two red brackets are equivalent to each other. So we're going to deal with the negative now, I guess. Dealing with that negative is the quotient log law. So this is going to be log base 7, sorry about the color change there, and in a big bracket, this is my argument. I'm going to have x squared times x, I'll put the power of 1 there, divided by x to the power of 5/2. Now, within the argument here, if I have x squared times x to the power of 1 divided by x to the power of 5/2, because they all have the same base, this is x to the power of 2 plus 1 minus 5/2, which is to say x to the power of 3 minus 5/2. 5/2 is 2.5, so I get x to the power of 1/2, which allows me to summarize this entire question as log base 7 of x to the power of 1/2. And what's really important about this is I can pick any value of x and put it into what I squared in black at the bottom here, and I would get the same value if I put it into the original expression. That's what writing, a single logarithm or simplifying something is. We haven't changed the value, we've changed the appearance, and that's a really important concept mathematically. I'm just going to grab this second example to a new page again, because these do tend to, lend themselves to a little more work. And in case you didn't miss it and you don't want to rewind, I'll just put that final answer up for half a second. And then we'll look at doing our second problem. Now, the restrictions can cause, a little bit of issues in these types of questions because they can be, it can be simple or they can be complex. Every argument has to be positive. So 2x minus 2, that's a weird 2, I got to redo that. So 2x minus 2 must be greater than 0. And the one that is tricky for students is that x squared plus 2x minus 3 must be greater than 0. This first inequality is typically not too bad to solve. I'm going to move the 2 over. I get that 2x must be greater than 2. When I divide by 2, I get that x must be greater than 1. And I'm just going to put a big and here. So we know that x has to be greater than 1. And, that's kind of the, one restriction on the variable. We have to determine the other restriction. Students struggle with this one. I get that. You learned it in Math 20-1. Honestly, you can go on my YouTube channel and look at how to solve for this. This is just, solving a quadratic inequality, and it's section 9 or chapter 9, 9.2 in Math 20-1. It might not be a bad idea to exploit this digital world and go take a look at that video. And I show several different ways of solving quadratic inequalities. The method that I like the best is a graphical technique. So I'm going to factor it. I get x plus 3 times x minus 1 must be greater than 0. And what I like to do is I like to picture my number line then as basically being equal to 0 at 2 points. It's equal to 0 when x is equal to negative 3, and it's equal to 0 when x is equal to positive 1. If I were to draw x squared plus 2x minus 3, it is a parabola that opens up. This parabola is greater than 0, and I'm going to draw this really specifically. It's not equal to 0, so we would put an open dot on positive 1, and it would be everything to the right of it. I would put an open dot on negative 3, and it would be everything to the left of it. So that inequality in black actually has two solutions. I could say that x must be less than negative 3, or x must be greater than positive 1. Now, here is the tricky part. What I wrote in blue and what I wrote in black must both be true. Now, because both of those inequalities must be satisfied, the solution is the overlap of those two inequalities. Well, where does x is greater than 1 and x is less than negative 3 or greater than negative 1, or greater than 1, sorry, overlap? It would be when x is greater than 1. So the restriction on our variable becomes x is greater than 1, and x would be any real number within there. And, you know, if you're having trouble, you know, picturing what this is, I can put x equals negative 4 into my second logarithm, but if I try to put x equals negative 4 into the first logarithm, it gives me log base 5 of negative 10. You cannot take the log of a negative number. And that's a really important consideration, that when we talk about, you know, the restrictions on the variable, it is simply the argument of each logarithm must be positive. That's the restriction, period. And that can get, you know, more complex as we look at, you know, more complex functions. All right, I'm going to cheat a little bit. I'm going to move that down, and then we're going to solve it, or, you know, we're going to simplify it, I should say. So to simplify this, I am just going to use my quotient log law. So that's going to be log base 5 of the positive logarithm divided by the negative logarithm. And then the last step in this question would be to simplify our log, which means factoring and looking for factors that are present in the numerator and denominator. So this will be equal to log base 5 of, I'll put the arguments in a big square bracket here. In the numerator, I'm going to have 2 times x minus 1. In my denominator, I'm going to have x minus 1 times x plus 3. And hopefully we all see what's going to cancel here. Oh, I forgot my bracket. And the simplified version of that statement is log base 5 of 2 over x plus 3. This is our answer. They definitely take a little practice, these types of questions. And, you know, one of the biggest things that students struggle with is, where do I start? And immediately, if I had to suggest a starting point, I would turn any coefficients on logarithms into an exponent inside the argument. Then I would try to work through my log laws. And then the last step is to try to simplify any complex argument that you might have ended up with, which is what I did in blue there, that last step.